So with linear response TDDFT, time-dependent density functional theory, this is going to end up being analogous to the time-dependent Hartree-Fock method called TDHF, which is sometimes called the random phase approximation. There are several different meanings sometimes for random phase approximation. So if you're reading that in literature, do kind of pay attention to which RPA they're referring to. Anyhow, TDDFT can often give you significantly improved results compared to the configuration interaction signal method or the RPA method, TDHF. So just to take a look at benzene, and all of these energies are given in electron volts. So experimentally, it's known that there are a number of different states with various different symmetries. If we compare CIS tends to overestimate a lot of energies, and we can see that compared to experiment that we tend to see some are quite highly overestimated, some are only a little bit overestimated, but they tend to be fairly high. There's a mean absolute error of 0.7. RPA is a little bit better, brings them down a bit, particularly this state, but still has an MAE of about 0.6. On the other hand, time-dependent BPW91 and time-dependent B3LIP, these have values that are a bit better in agreement with experiment. Now, in this case, we've got ones that are overestimating. In this case, we've got ones that are underestimating. This one's pretty close to right on. Some of these are pretty close again. So overall, the MAE values in this case are about 0.1. And lots of times, accuracies for time-dependent density functional theory can be within about 0.3 eV, maybe 0.5 EV, but you can get things that are pretty close, or you can get things that are a little bit further away. But they will tend to be better than CIS. And again, CIS will tend to overestimate energies. With hybrid functionals, like many times with hybrids, you never know if something's going to be a little bit more like the Hartree-Fock-like results or more like a pure GGA. Pure GGAs will often tend to underestimate the energies. So with a hybrid, since you're kind of averaging between a pure GGA and a Hartree-Fock-like method, you can end up getting something that's in between. Sometimes that gets really close. In this case, it's overestimating. So it just depends a little bit on the particular state, the particular hybrid functional, how well Hartree-Fock and pure GGA functionals do for that. Okay, so just a few considerations for TDDFT. So if we're going to do linear response TDDFT, we need the cone sham orbitals and eigenvalues. Those eigenvalues go into the equations, and of course we need them. We also need to calculate a number of integrals that involve the cone sham orbitals. So many of those things that were not needed for ground state DFT, so there are additional integrals that are needed that involve the unoccupied orbitals. Another thing we need is the exchange correlation kernel. So that's the second derivative of the exchange correlation functional. So usually we have the first derivative, but we need to have a second derivative for linear response TDDFT. So it depends on the functional. For many of them, this has been derived, but it's not available for every single thing. So we can't always do linear response TDDFT for everything. In those cases, doing real-time TDDFT where the density is propagated can sometimes be better. But again, linear response TDDFT is very good for getting those excitation energies with usually not as much cost as real-time TDDFT, at least for smaller systems. All right, so TDDFT, when we want to think about what it does well for, it's going to tend to be the lower energy excitations. Part of that is because the orbital energies for the higher energy orbitals are just not as good as higher unoccupied orbitals. Also, for a number of reasons, it's good if the excitation energy is less than the ionization potential. For a practical reason, one might expect ionization to occur if the energy is better, but TDDFT also does better than getting that accurately. And it's also better if the excitation doesn't go into orbitals that happen to have a positive orbital energy. Another thing to keep in mind if you're doing TDDFT is that if you're using a pure DFT functional, there are problems with charge transfer excitations. And this really comes from the self-interaction error that's inherent in DFT. So there are many different issues that can happen, but basically you end up getting some spurious low energy states, and they happen to have a really high oscillator strength, so they look really important at low energy where you're likely to see them, but they don't actually exist at that energy or with that large of an oscillator strength. So the fix for that is to use these long-range corrected functionals. The idea with a long-range corrected functional is it's going to switch over to Hartree-Fock exchange and get the proper 1/R12 type of relationship when you've got these large values of R12. And so these long-range corrected functionals do much better at the type of charge transfer states that are issues for TDDFT.